Mountains kill. Not slowly, not kindly. They drop 100,000 tons of snow at 290 kilometers per hour and erase villages in 60 seconds. You hear stories about white powder clouds that look beautiful until they hit with the force of a freight train made of concrete. You see photos of rescue crews digging for days. But nobody talks about how many different ways snow decides to murder you. Slab avalanches, powder avalanches, wet slides, ice falls, cornice collapses, slush flows. Each one moves differently, each one kills differently. Which type buried 31 people in an Austrian village in under a minute? Which one can flow from slopes gentler than 3 degrees? Which formation lurks in your snowpack for months waiting to collapse? If you value documented snow science and mountain survival history like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual, using sources from the Swiss Institute for Snow and Avalanche Research, SLF peer-reviewed studies, published in the Journal of Geophysical Research, Earth Surface, in 2018 in the Colorado. Avalanche Information Center, National Accident Database, tracking U.S. deaths since 1950. These aren't general mountain safety sites. These are the organizations that measure powder cloud velocities with pylon-mounted sensors and calculate the exact tonnage that hits buildings. Now back to the information. 4 meters of fine powder snow piled up through 3 separate Atlantic storm systems over 3 weeks. Northwest winds, Arctic air meeting tropical moisture. A melt crust formed between storms, upper layers melting during daytime. Refreezing at night. The village sat in a green zone, supposedly safe. No avalanche had reached that far in living memory, possibly not since the late 1600s. At 1559, the crust failed. The powder avalanche that followed measured 50 meters high, traveled at 290 kilometers per hour. The Swiss Federal Institute measured similar events and found powder avalanches create a saltation layer between the dense flow and the airborne cloud. That layer wasn't understood before Galtur. It's why buildings shattered instead of just getting buried. The avalanche contained a 3-part structure: dense basal layer, turbulent saltation zone in the middle, with air particle mixture densities reaching 20 kilograms per cubic meter, powder suspension cloud on top. The saltation layer moved snow from dense flow to powder cloud, created coherent structures 3 to 14 meters long, 10 meters high or more. Those structures traveled 60% faster than the front, maintained snow clusters in suspension for several seconds, generated massive forces at heights where nobody expected impact. 57 people buried, 31 dead by the time rescue crews arrived, 6 locals, 25 tourists, 6 houses destroyed, 18 damaged. The supposedly safe zone took the worst hit. The avalanche forecasters at SLF rated danger as very large for Bernese Oberland, only large for that section of Valais. A mountain guide with 25 years' experience checked the snow structure at Lesage after morning services, told the mayor conditions looked acceptable. The avalanche hit anyway. 12 dead, 13 buried, 8 houses destroyed, 4 chalets, 5 barns, multiple alpine huts completely gone. Between January 27th and February 25th, 1999, over 5 meters of snow fell on northern alpine slopes, more than an entire typical winter in 30 days. Danger levels 4 and 5 remained in place for extended periods. The Swiss recorded around 1,400 destructive avalanches that winter. Annual average is 136. The 1999 season tallied over 70 deaths across Austria, France, Italy, and Switzerland, one of the deadliest avalanche periods of the 20th century. The winter of 1951 saw 235 deaths in Austria and Switzerland alone, called the Winter of Terror. But 1999 proved modern villages aren't safe either. Turbulent suspension of airborne particles, less than 5% snow by volume. The rest is air. Forms when dry slab avalanches accelerate down steep terrain, fracture into fine particles, become suspended in turbulent air currents. Speeds regularly exceed 250 kilometers per hour, can reach 300. The Vallée de la Sion test site in Switzerland has pylon-mounted sensors at multiple elevations. Load cells measure impact pressures. Optical sensors track particle velocity. Capacitance probes measure cloud density and cluster size. Buried radar tracks snowpack thickness. Data from powder events shows distinct flow regions with density stratification. At the head, highly fluctuating impact pressures weaken with elevation. Vertical velocity profiles evolve rapidly along the flow. Surface snow layers of light, cold, cohesionless snow erupt into turbulent, inhomogeneous, recirculating frontal cloud. Region. For hundreds of meters behind the head, cloud stratification sharpens with deposition of suspended particles. Denser basal flow of increasing thickness entrains warmer, deeper snowpack elements. Toward the tail, vertical profiles become uniform. Impact pressure and fluctuations decrease, flow thins, erosion of snowpack becomes negligible. Powder avalanches can travel 4 kilometers or more on slopes averaging 30 degrees. Large events where powder cloud sustains momentum over gentle terrain show the lowest friction coefficients. Air cushioning effect. Typical values for basal shear. Stress use density around 200 kilograms per cubic meter for the powder. Influenced flows. Friction angle tangent approximately 0.1 to 0.3 for dry snow. Turbulence coefficient 300 to 1,000 meters per second squared. These numbers come from back calculations of observed events. Field data calibration, not theory. Forms when bonded snow layer sits on top of weak layer over sufficiently large area. Requires slope angle minimum 30 degrees. Bonds holding slab fracture at approximately 220 miles per hour, according to Bruce Tremper's field. Measurements. 352 kilometers per hour. Appears to shatter like glass. Triggering starts with small fracture and weak layer. Initial failure rapidly propagates across it. Fracture propagation depends on weak layer properties and slab characteristics above. Typical size of slab released by winter sport participants is 50 meters wide, 150 to 200 meters long, average depth 50 centimeters, volume around 2,000 cubic meters, 400 tons, reaches 20 miles per hour within first 3 seconds, accelerates to 80 miles per hour after 6 seconds, 130 kilometers per hour. Person who releases a slab is often within perimeter. Caught in the avalanche. They can occur only when bonded layer exists over weak layer. The weak layers are the key. Surface hoar, near surface facets. Depth hoar forms at base of snowpack when shallow snow sits on ground under cold, clear skies. Strong temperature gradient from relatively warm ground. Snow crystals transform through metamorphosis into loose, dry, sugary crystals. Large angular grains. Chains of cup-shaped crystals up to 10 millimeters. Lack cohesion, lack strength. Bane of snowpack. Continental climate areas notorious for this. Rocky Mountains of Colorado. By February, entire snowpack may consist of weak, faceted snow. In northern Utah, Wyoming, Idaho, Montana, where snowfall usually greater depth hoar, typically early season phenomenon. Sierra Mountains of California can still form early season, especially east side, where snow often dry and shallow. Forms primarily on shady northerly aspects where temperature remains coldest. Snow receives little to no solar radiation. Cold, dark places. Faceted crystals develop and remain for long periods. Never trust a depth hoar snowpack. Old saying among avalanche professionals. Once formed can persist entire season, can be triggered remotely, can fail weeks after last storm. Spatial variability increases as season progresses. Depth hoar persists where snowpack remains shallow. Shady, mid-elevation slopes, areas of frequent wind scour, rocky outcroppings, bottom of basins where cold air pools. Surface hoar is winter's version of frost. Frozen dew, feathery crystals on snow surface when air above cools to frost point. Recipe for formation is specific. Clear, cold sky, high relative humidity, relatively calm winds. When conditions align, surface hoar forms very quickly, like frost on windshield. Equally challenging for fragile feathers to survive on surface. Wind, rain, sun, sloughs can destroy before burial. Spatial patterns fickle and pockety. May find in one bowl, but not next. One snow pit, but not 10 yards away. Ingredients for formation and preservation most often come together in sparsely gladed or open wind-protected terrain. Colder aspects well below windy ridges. Common for surface hoar to form on specific elevation band. Bathtub ring effect. Once buried, gets harder to identify problematic slopes. Thin gray stripe in snow pit, highly variable presence, can cause persistent slab instabilities for months. Common weak layer in avalanche accidents. Most troublesome terrain may not be classic alpine start zones, rather sparsely gladed slopes lower on mountain, wind-sheltered areas with incoming storms. Because surface hoar easily destroyed by wind, it's preserved where wind doesn't reach. Near surface facets form between storms, smaller than depth hoar, 1 to 2 millimeters. When snowpack becomes deeper, only top 15 to 20 centimeters, affected by air temperature fluctuations. When surface subjected to fluctuating daytime and nighttime heating and cooling cycles, called diurnal fluctuations, the surface begins to facet. Longer the exposure to temperature fluctuations, weaker the surface becomes. This persistent weak layer responsible for nearly 60% of all avalanche accidents in southwest Montana, according to Carl Birkeland's 1996 study. Forms in between storms, sits waiting, days, weeks, months sometimes. Low speed due to friction between sliding surface and water-saturated flow. Despite low speed, 10 to 40 kilometers per hour, capable of generating powerful destructive forces. Large mass and density. Body of flow can plow through soft snow. scour boulders, earth trees, vegetation, leave exposed and scored ground in track. Can be initiated from loose snow releases or slab releases. Only occur in snowpacks, water saturated, and isothermally equilibrated to melting point of water. 0 degrees throughout. Allows meltwater and rain to seep through entire snowpack. Usually occur when warm air temperatures, sun, or rain cause water to percolate through snowpack. Decrease strength of snow, change mechanical properties. Travel more slowly than dry snow, like 1,000 concrete trucks dumping loads at once, rather than hovercraft movement of dry avalanche. Typical wet avalanche travels 15 to 30 kilometers per hour. On steeper terrain can go nearly as fast as dry avalanche, harder for person to trigger than dry slide. Don't account for as many fatalities as dry snow avalanches. Still account for sizable percentage, especially in maritime climates. Especially dangerous to climbers, can do considerable damage to property forests, cause significant hazards on highways. The extreme violence inside flowing debris grinds snow into finer and finer particles. Even if snow started light and fluffy becomes very dense by time it stops. Large avalanche, starting with density 5 to 10%, can end up 30 to 40% at bottom. Dense snowpacks very tightly when everything stops. Small grains sinter coalesce much more quickly than large grains. Tiny grains, making up avalanche debris, can sinter 10,000 times faster than larger grains of initial slab. All kinetic energy liberated on way down heats up snow slightly. Creates small drops of liquid water on surface of ice grains. Avalanche debris seizes up like concrete the instant it comes to stop. This makes rescue extremely difficult. Buried victims cannot move, cannot dig themselves out. Cannot breathe easily through dense compacted snow. This research comes from David McClung and Peter Scherer's Avalanche Handbook Field Measurements and the European Avalanche Warning Services Classification System updated January 31st, 2025. These sources track avalanche mechanics with precision equipment measuring flow velocities, impact forces, and failure mechanisms in real conditions. Not laboratory estimates, actual mountain data. Now back to the types. Gliding avalanches are the unpredictable ones. Release of entire snowpack as a result of gliding over ground. Can be composed of wet, moist, or almost entirely dry snow. Occur in very specific paths. Slope steep enough. Ground surface relatively smooth. Often preceded by full depth cracks, called glide cracks. Time between appearance of crack and avalanche varies, seconds to months. Cannot be triggered by person. Nearly impossible to forecast. Pose hazard extremely difficult to manage. Released naturally when friction decreases at interface with ground. Snow at base of snowpack becomes moist. Water penetrates lowermost layer 2 different ways. In midwinter, snowpack usually cold and dry. Becomes moist from underneath. Either warm ground melts snow above, or snow absorbs water from moist ground. Can occur any time day or night in midwinter. In spring, snowpack reaches temperature 0 degrees throughout. Isothermal. Allows meltwater and rain to seep through entire snowpack. Moisten base from above. Major problem for transport routes, especially snowy winters. Only secondary significance for winter sport enthusiasts because cannot be triggered by people. Glide cracks, significant indicator. Recent glide avalanches, another sign. Safe travel relies on identifying and avoiding those slopes. Predicting release, very challenging. Some slopes hold cracks for months without releasing. Others go within hours of crack appearing. Gather more loosely bonded snow crystals from surface as descend. Gradually fan out. Inverted V pattern after the fact. Starting from point, spreading downhill, do not usually do major structural damage or bury people, although possible. More often, knock person off feet, carry downhill. Deadly if carries into trees, over cliff, into terrain trap. Terrain traps, typically small gullies. Even small avalanche can quickly fill small gully. Bury you a couple meters under snow and gully bottom. Dry, loose avalanches generally require slope angle of 40 degrees. Most relatively harmless to people, unless caught and carried into terrain trap or down long slope. Wet, loose avalanches occur during significant warming, strong solar radiation. Rain on snow. Surface layers slide easily, water visible between ice grains. Fresh rollerballs, little snowballs falling off trees, and cliff bands indicate snowpack surface getting weak. If loose, wet avalanche entrains very large amount of snow, can run long distances on low angled terrain. Can reach considerable size in continuously steep terrain. Density of slush, near 1,000 kilograms per cubic meter according to Norwegian studies from 1980s. Bearing capacity almost nil. Surface often shows marked blue-gray color indicating water saturation. Less than 10% of avalanche fatalities attributable to loose snow avalanches. Many deaths occur in summertime when mountaineers in steep terrain swept along and fall. Winter sport participant who triggers loose snow avalanche, seldom buried because slides down slope away from them. Usually releases only small snow masses, but slough management in extreme terrain essential technique for skilled riders. Must ski fall line for short distance, then shift laterally on face. Continue skiing fall line there. Slough from original fall line continues down face next to them at comfortable distance. Overhanging massive snow forms as wind moves snow over sharp terrain feature, ridge crest or summit, deposits snow on downwind leeward side, range from small wind lips of soft snow to overhangs of hard snow 30 feet 10 meters or taller. Can break off terrain suddenly and unexpectedly, sometimes triggered from distance. Overhung cornices can pull back further than expected onto flat ridge top, catch people by surprise, even on flat ground above slope. While large cornices quite destructive by themselves, even small cornice deadly if carries you over cliff or rocky terrain. Impact from cornice fall can easily trigger slab avalanches on steep slopes below. Cornices develop whenever snow available for transport and wind sufficiently strong. Ideal wind speed for cornice development 15 to 25 miles per hour. Stronger wind speeds move snow further downslope. Creates other hazards. Cornices can form quickly with favorable wind speeds and abundantly available snow. Typically following recent storm, multiple wind events over time generate large overhanging cornices comprised of numerous hard snow layers. Often interspersed with soft, weak snow layers or hollow tunnels. Form on downwind leeward side of sharp terrain features. Ridges above treeline most common locations. Also form downwind of vertical ridge lines and tops of couloirs. Process called cross-loading. Brief wind event following storm snow quickly generates soft cornices on lee of any terrain feature. Soft wind cornices easy to trigger artificially. If not large, often manageable by themselves. Soft cornice fall, however, can run long and fast. Quickly entrain additional snow, results in much larger and more dangerous avalanche. Longer wind event, typically lasting at least day, generates larger, harder cornices. Stiff cornices may appear supportive of human but cannot be trusted. Additional weight from more snow load or human can result in crack that easily propagates. Cornice fall can happen from distance, remote release. Cornices build to very large sizes through winter, most likely during periods of significant temperature, warm-up, or rapid cornice growth due to wind loading. In some parts of Svalbard, Norway, cornices responsible for around 45% of all avalanches, according to research from WSL Institute for Snow and Avalanche Research published recently. Avalanches triggered by collapse of cornice threaten local infrastructure and people's lives. Travel cautiously on corniced ridgelines. Give cornices or unknown edges wide berth. Limit exposure to slopes below cornices. Cornices break further into ridge crest than you might expect. Seracs are blocks or columns of glacial ice, formed by intersecting crevasses on glacier, house-sized or larger, dangerous to mountaineers, may topple with little warning. Even when stabilized by persistent cold weather, can be impediment to glacier travel. Found within icefall, often in large numbers, on ice faces on lower edge of hanging glacier. Notable examples, well-known obstacles on world's highest mountains. K2 at the bottleneck, Kanchenjunga on border of India and Nepal. Significant seracs in Alps on northeast face of Pizrozk, north face of Dent d'Herens, north face of Liskam. April 18, 2014, Mount Everest. Serac broke off western spur. Ice avalanche killed 16 climbing Sherpas in Khumbu icefall, same icefall where 1970 Mount Everest disaster took place. Serac estimated 34.5 meters thick. Mass of 14,300 tons. 13 bodies recovered within 48 hours. Search and rescue operations called off due to too much risk. 3 victims still buried in roughly 80 to 100 meters of snow and ice. 9 other guides injured. 3 required intensive care hospitalization. The Khumbu Glacier moves estimated 0.9 to 1.2 meters down flank of Mount Everest every day. Ice entering fall takes approximately 4.3 years to emerge at base. 600 meters lower, 1.5 kilometers away horizontally, speed of ice flow and precipitous elevation drop create Bergschrund, characterized at top by massive transverse blocks, calve off upper glacier, creating gaping crevasses over 100 meters deep, often over 15 meters 50 feet wide. Official Himalayan database records 44 deaths in icefall between 1953 and 2016. No deaths recorded between 2017 and 2021. Most climbers try to pass through icefall before sunrise, when usually less mobile due to freezing and nighttime cold. As sunlight warms, area ice melt causes friction within structure to decline, increases rate of flow, hence crevasse opening and ice block or serac collapse. Most dangerous time to cross, fall generally mid to late afternoon. In 1990, earthquake caused block of Sirac to fall off Lennon Peak, triggered Avalanche hit camp, killed 43 people. August 2008, K2 disaster collapse of large seracs responsible for at least 8 of 11 mountaineers' deaths. July 3rd, 2022, Sirac collapsed on Marmolada Glacier, Italy. Caused avalanche, killed 11 alpinists, injured 8. Seismic energy released comparable to earthquake of 0.6 magnitude. Area had seen early heat wave. Summit recording abnormally high temperatures around 10 degrees Celsius. Collapse occurred near Punta Rocca at height 3,309 meters, route utilized by climbers to reach top peak. August 5th, 2024, Mont Blanc du Tacul. Serac collapsed at 3 a.m. Altitude 4,100 meters on peak's north face. Block of ice fell above group of 15 mountaineers. Triggered rock avalanche reached Col du Midi. Hit line of climbers on way up Mont Blanc via popular Three Peaks route. 1 dead, 4 injured, French national 57 years old. North side of Mont Blanc du Tacul, infamous for frequent avalanches triggered by Serac fall. Between 2000 and 2022-13, died on section called Épaules du Tacul alone. 8 in 2008. 2 in 2013. 3 in 2016. Risk of death from Serac collapse at Tacul calculated as 8.3 times 10 to the negative 5, based on 6,770 passages recorded during summer 2. 1017 and 31 Serac falls unrelated to temperatures. About 1 in 10,000 chance per crossing. Ice falling off west shoulder of Everest, widely considered most pressing danger in modern times. 1976. Sherpas killed supporting Japanese expedition. 2014-16 Sherpas died when hanging Serac released as they waited for ladder replacement over crevasse. They were ferrying loads to higher camps. While in autumn 2019, house-size piece of ice barely hanging 3,000 feet above icefall. All teams attempting Everest that season ended efforts. Feared Serac would release just as they passed underneath, similar to 2014. Caused when water reaches critical concentration in snowpack. More water inflow than outflow. High water concentration weakens cohesion of snow crystals, increases weight of snowpack. Released when component of force of gravity parallel to slope generates hydraulic pressure gradient, exceeds tensile strength and basal friction of snowpack, lower frequency than avalanches, higher water content, more laminar in flow, lower velocity. Most commonly occur at higher latitudes in winter during high precipitation, in spring during high snowmelt, generally occur during rapid spring breakup in Arctic and subarctic alpine regions. Snowpack becomes saturated with meltwater, characterized by slow-moving destructive debris. Flows from much gentler slope angles than other avalanche types. Can cascade from slopes as gentle as 3 or 4 degrees, practically level ground. Considerable earth and rock material may also be carried downward. Sometimes churn along slowly, other times move faster than 25 miles per hour, 40 kilometers per hour. Small slush flow may be only a foot or so thick. Those thicker than 50 feet have been observed, owing to high density of slush flow due largely to high water content flows, have high momentum, like moving locomotive, almost unstoppable, therefore highly destructive. Most dangerous times when temperature risen to about 40 degrees Fahrenheit, 5 degrees Celsius, and remained there 24 or more hours. Afternoon, worst time for slush flows. June 11, 1953. Slush flow struck small coal mining settlement of Longyear Bayan, Spitsbergen. Summer 1980 road grader on Alaska. Pipeline haul road struck by slush flow. Caused no damage other than pack icy slush around grader's engine. Driver lucky flow was small. Slush flows known to occur in Brooks Range, mountain areas of Alaska's Seward Peninsula, occasionally in Talkeetna Mountains near Anchorage. Snow cover instability results from basal accumulation of water, enhanced by presence of impermeable icy layer rock surface or frozen ground. Intense thaw in spring may produce more meltwater than can drain through snow. Cause release of slush avalanches. Water saturation often indicated by appearance of marked blue-gray color on surface. Heavy rainfall on cohesionless new snow immediately before release, most striking feature in Norwegian studies. Only one exception caused by intense thaw in spring was observed, when avalanches released in areas with coarse-grained snow cover developed during period of low temperature. Starting zones had, during previous 24 hours, received 70 to 100% of recorded daily maximum precipitation for month. Amount of precipitation for previous 3 days was 7 to 10 times higher than 3-day mean based on recorded monthly normal. Corresponding values for avalanche situations, characterized by repeated changes between snowfall rain and cold, dry weather, were 40 to 60% and 3 to 6 times of mean monthly normal. Main starting zones: drainage channels, sloping bogs, depressions, and open fields. Channel-like scar-like or bowl-like features appeared in snow cover due to avalanche release. 3 main types of release identified: sudden release from crown surface, drainage of snow-embanked water, saturated snowfields through narrow outlets, rapid headward growth from first point of release. Slush flows cascade from slopes barely tilted. Each type has signature. Each kills its own way. The saltation layer at Galtour wasn't understood before radar measurements at Vallée de la Sion, impact pressures at different elevations, velocity profiles evolving, coherent structures moving 60% faster than front. The science comes from disasters, from villages buried, from climbers who didn't come home, from Sherpas ferrying loads when ice let go. Over last 10 winters, average of 27 people died in avalanches each winter in the United States, according to Colorado Avalanche Information Center database. That's confirmed fatalities, investigated accidents. In 2023, 30 people died from avalanches in U.S., most recent year on record. In 1999, over 70 died across Alps, Galtour 31, Evelyn 12, Valzur 7, Montreuil near Chamonix 12 on February 9th. Most deaths from slab avalanches, 90% of victims. The person caught usually triggered it themselves or someone in their party did. 95% of cases victims trigger slab avalanches themselves, according to Ortovox Safety Academy. Data. In Alps, around 115 people die in avalanches yearly, most in slab avalanches. Every year, same pattern. Person goes onto slope, weight adds load to weak layer, fracture propagates, slab releases, person within perimeter, caught. Buried. Even medium avalanche, typical size, 50 meters by 150 meters, depth 50 centimeters can kill. Many fatal slides, classified as medium. Large avalanches cross flat terrain well below 30 degrees over distance less than 50 meters. Can bury and destroy trucks and trains, destroy fairly large buildings and small areas of forest. Size 5 avalanches largest category can destroy 40 hectares of forest. Railways, large buildings, run out onto valley floor causing major devastation. These don't happen often. Size 2 and 3 kill most people, medium and large. Just big enough, just fast enough. Temperature gradient does the damage. Difference in temperature over distance. If snowpack differs more than 1 degree Celsius per 10 centimeters of snow depth, strong temperature gradient present. Conditions cause individual grains to become angular and faceted, form weak layers that persist, cannot see them from surface, have to dig pit, test snowpack, look for thin gray stripe, feel for sugary layer. Or wait until slope collapses beneath you, woompfing, shooting cracks, signs that weak layer failing, remote triggering possible, crack propagation over long distances common. Can trigger avalanche from flat terrain below above or to sides of steep slopes, even well down an avalanche path. After dozens of tracks have crossed slope. Tracks on slope, not indicator of stability, person before you got lucky. You might not. Scientists measure this now. Pylon-mounted sensors, load cells, optical velocity tracking, radar measuring snowpack thickness, capacitance probes for density, temperature gradients recorded, crystal formation documented. Weak layer development tracked, but cannot predict exact location or exact time of individual avalanche, cannot say the slope will go at this hour, can only say conditions favor failure, can measure after disaster, calculate forces, determine flow mechanics, understand what killed, build better hazard maps, erect avalanche barriers, steel fences on mountainsides above villages, 300-meter dam protecting Galtour now, hazard zones redrawn. Green zone that took worst hit in 1999, now higher risk zone. Former red zones expanded. After Galtour, Austrian Federal Service for Torrent and Avalanche Control developed project, including avalanche barriers and snowpack stabilizing. Structures. Main parts finished. Intercantonal early warning and crisis information system introduced in Switzerland 2002 after Avalanche. More measurement stations installed, almost doubled amount compared to 1999. Wider coverage and measuring network. System updates. Winter 2017-18 tested improvements, heavy snowfall. January 15th, more intensively. January 21st to 23rd. Over 3 meters, fell some places. Highest danger level 5, very high in force for 2 days. Not as extreme as 1999, but important test. Showed measures implemented after 99 having desired effect. Nevertheless, no absolute safety. Even today, neither exact location nor exact time of individual avalanche can be predicted. Analysis published spring 2019 confirmed defensive measures working. But working means fewer deaths, not 0 deaths. Mountains still kill. Still drop snow that shatters buildings. Still bury climbers under 15-meter thick seracs. Still send coherent structures through powder clouds at velocities 60% above front speed. still create persistent weak layers that wait months to fail. 60 seconds from fracture to complete devastation. The research from that disaster led to understanding saltation layer mechanics, led to pylon networks measuring actual forces in real avalanches, led to models that can calculate how deep snow will bury infrastructure. But Galter was supposedly safe. Green zone, outside red zone boundaries. Prior to 1999, Poznan Valley had not seen avalanche on that scale in living memory. Not since late 1600s. Hazard zoning dependent on historical record. When historical record, incomplete zoning wrong. Climate changes, weather patterns shift. What couldn't happen before happens. Family members demanded to know why avalanche penetrated supposedly safe zone. Devastated Galter. Answer was honest and terrible. Historical data didn't include this. Return interval over 200 years. Multi-day snowfall totals in early 1999 that rare. That dangerous. Cannot plan for what hasn't happened in anyone's lifetime. Can only respond after. Extend zones. Build barriers. Hope it's enough. Install more sensors. Measure more precisely. React faster. But cannot predict the unpredictable. Cannot stop the unstoppable. Can only document after bodies recovered. After debris cleared. After measurements taken. Then publish studies. Update models. Improve forecasts. Save some lives next time. Not all. Never all. Because mountains don't negotiate. Snow doesn't compromise. Physics doesn't care about hazard zones or safety plans or green, yellow, red designations. Temperature gradient forms weak layer. Additional load exceeds strength. Fracture propagates. Avalanche releases. Simple as that. Terrible as that. Mostly out of bounds skiers. Snowmobilers increasing. In US over last 45 years, total 440 victims killed in 324 fatal avalanches. 87.7% fully buried. 4.7% partially buried. 7.6% not buried. Average age 27.6 years. 87.3% men. Climbers 25.5%. Backcountry skiers 22.7%. Out of bounds, skiers 10%. Snowmobilers 6.8%. In bounds, skiers 5.2%. Residents 4.5%, ski patrollers 3.6%, workers 3.6%, motorists 3%. Over 45-year study period decreases in deaths of inbounds, skiers, highway workers, and motorists, increasing fatalities among out-of-bounds skiers, snowmobilers, ski patrollers, and backcountry skiers. The decrease in deaths among groups that benefit from avalanche control programs supports benefit of avalanche prevention strategies. The increase among recreational backcountry users suggests problem getting worse. More people going into uncontrolled terrain, taking more risks, or maybe terrain getting more dangerous. Climate warming, snowpack characteristics changing, rain on snow events increasing, wet avalanche cycles occurring earlier in spring. Warm, wet snowpacks likely to increase in frequency due to climate change also make avalanche burials more deadly. Warm snow has higher moisture content, denser than colder snow. Denser avalanche debris decreases ability for buried person to breathe. Amount of time before run out of oxygen. Increases likelihood of death by asphyxia in event of burial. Storm precipitation intensity expected to increase, likely to lead to more days with enough snowfall to cause snowpack to become unstable. Moderate and high elevations may see increase in volatile swings from one weather extreme to other. More freeze-thaw cycles, more melt crust formation, more weak layers developing, more persistent instability. But most accidents come from human choices. Decision to enter terrain, decision to cross slope, decision to go despite warning signs, whomping collapses, shooting cracks, recent avalanche activity, signs of instability ignored or missed. Our conditions look fine until they don't. Weak layer spatial variability means adjacent slopes behave differently. Check one pit, find nothing concerning. 10 meters away, buried surface hoar waiting. Check track laid down by someone earlier. Follow their line, different loading pattern, different timing, weight sufficient to tip scales, house of cards, collapses, slab releases, within perimeter, buried, search begins, probe lines spiral out from strongest transceiver signal. 25 centimeter increments, looking for soft area at probe tip, victim's body or equipment, digging starts, race against time. 15 minutes critical window. After that, survival rates plummet, brain without oxygen. Body cooling in dense snow. Debris seized like concrete. Cannot self-rescue. Cannot dig out. Cannot move. Cannot breathe through compacted mass. Need someone to find you. Need them fast. Need them to know where to dig. Need luck. Lots of luck. Rescue dogs prove value. Heiko at Galter saved many lives. Jack the Labrador Alsatian Cross buried under snow 24 hours. Survived. Most don't survive 24 hours. Most don't survive 6 hours. Most die in first hour if not found. If buried deep, if debris heavy, if no air pocket, if injuries from impact, if trauma from ride down, trees, rocks, cliffs, terrain traps, small gullies that fill completely, bury you meters deep in small space. Even small avalanche fills small gully, even size 1 or 2 avalanche kills in terrain trap. Knowledge doesn't protect, can measure weak layer crystal size, document temperature gradient, calculate load threshold, test stability, but cannot remove weak layer, cannot strengthen it, cannot make it safe, can only avoid or accept risk. Most choose to go, most survive, some don't. Those who don't become data points, case studies, accident reports, entries in database, names on memorial, photos in news, stories told at bars, warnings to others, which usually don't work. Because everyone thinks it won't happen to them. Everyone thinks they'll be the exception. Everyone believes they can read the snow better, choose safer lines, react faster, until the slope releases and they realize they were wrong. By then, usually too late. The day 31 people died because weather patterns aligned exactly wrong. Atlantic storm forming 4,000 kilometers away. Turbulent warm air from tropics heading north, cooling, swinging back toward Europe. Combined with cold Arctic air from north, very dry light snowfall exceeding 4 meters. 3 separate precipitation periods roughly a week apart, each dumping over a meter of snow. Northwest winds piling snow to increasing depths. Bonding with underlying ice of melt crust, staying in place longer than usual, new snow falling, melt crust becoming unstable, weight increasing. Until at 15:59 on Tuesday afternoon, the crust failed. 60 people buried, 31 dead. 6 houses destroyed, 18 damaged, green zone destroyed, supposedly safe location devastated. Return interval over 200 years, meaning in modern statistical terms, this storm combination and resulting avalanche, so rare it happens on average once every 200 plus years. Cannot prepare for events that rare, cannot design defenses, cannot maintain constant vigilance, cost too high, disruption too great. So accept risk, live in mountains, enjoy beauty, take precautions, build some barriers, monitor conditions, hope it doesn't happen. Until it does, then respond, rescue, rebuild, remember, document, learn, improve, prepare for next time. Because there will be next time. Maybe not in 200 years, maybe sooner. Maybe a different location, different mechanism, different weak layer, different loading event. But mountains will drop snow again, slopes will release again, people will die again. That's not pessimism, that's physics, that's gravity. That's the nature of snow on steep slopes in alpine terrain with temperature gradients forming weak layers, and additional loading exceeding strength and fractures, propagating at 350 kilometers per hour, shattering cohesive slabs that accelerate to 80 miles per hour in 6 seconds, carrying 400 tons of snow that seizes like concrete when it stops burying people who cannot dig themselves out, cannot breathe through dense debris, cannot survive without rapid rescue. That's avalanches, all types, all mechanisms, all outcomes. Beautiful until they kill you, quiet until they're not, seemingly stable until fracture line appears. Then it's too late. You're in it. You're going down. You're hoping someone saw. Hoping they have beacon. Hoping they can dig fast enough. Hoping you get air pocket. Hoping debris not too deep. Hoping trauma not too severe. Hoping you're the lucky one who survives. Most are lucky. Some aren't. Those who aren't taught us everything we know. Their deaths led to sensors, to measurements, to understanding, to models, to better forecasts, to safer zones, to more awareness, to this knowledge, to these words, to this documentation. So others might recognize signs, might make better choices, might avoid slopes that want to slide, might survive where others didn't. That's all we can do. Measure, document, teach, hope, because we cannot stop the mountains, cannot change the physics, cannot eliminate the risk, can only understand it better, respect it more, survive it when possible, mourn those who don't, keep measuring, keep learning, keep trying, keep surviving. The Khumbu icefall moves 1 meter per day. Seracs topple with no warning. Surface hoar forms overnight. Depth hoar develops slowly. Slush flows cascade from 3-degree slopes. Cornices break back further than expected. Wet slabs flow like concrete. Powder avalanches reach 300 kilometers per hour. Slab fractures propagate at 350. Weak layers persist for months, each mechanism documented, each behavior measured, each death recorded. Not to sensationalize, not to frighten, to inform, to educate, to help people understand what they face when they enter avalanche terrain. Because mountains are beautiful, snow is alluring, steep slopes are tempting. But physics doesn't care about beauty, Gravity doesn't care about temptation. Temperature gradients don't care about your experience level. Weak layers don't care about your intentions. Avalanches don't distinguish between expert and novice. Don't spare the cautious, don't wait for the reckless. They just go when conditions align, when loading exceeds strength, when fracture reaches critical propagation. They go fast, hard, final. Not to keep you out of mountains, to help you come home. The science exists. The data is there, the patterns are clear. Slab avalanches kill 90%, form on slopes 30 degrees or steeper, release when weak layer fails. Powder avalanches travel fastest, create 3-layered structure. Impact with forces nobody predicted before measurements existed. Wet avalanches move slower, pack denser, can be just as deadly. Ice avalanches drop tons without warning. Kill climbers ferrying loads, cornices break further back than expected. Trigger slides below, slush flows move on gentle terrain. Spring killers in Arctic regions, loose snow avalanches start from point. Usually harmless, unless terrain trap involved. Each type different, each deadly in specific ways. But all avalanches share common thread. They're mass movements of snow driven by gravity, influenced by temperature, modified by wind, shaped by terrain, triggered by loading. Whether that loading comes from new snow, from wind deposition, from temperature change, from rain, from human weight, doesn't matter. Load exceeds strength. Failure occurs, avalanche releases. Rest is just details. Velocity, density, distance, impact force, burial depth. These matter for rescue, matter for survival, matter for prevention. But underlying cause always same. Snow that wants to slide will slide. Question is when. Question is whether you're there. Question is whether you recognize signs, whether you make right choice, whether you turn back, whether you wait, whether you go different route, whether you survive. Those who measure avalanches cannot predict your specific avalanche on your specific slope at your specific time. They can only tell you conditions favor failure, tell you weak layers present, tell you loading occurring, tell you danger level high. The decision remains yours. The risk remains yours. The outcome remains yours. Choose wisely. Respect the snow. Trust the science. Question the conditions. Avoid the terrain when doubt exists, because you cannot negotiate with avalanche. Cannot reason with it. Cannot stop it once started. Can only not be there when it goes. That's the only reliable prevention. Everything else is risk management, mitigation, probability reduction, but not elimination. Never elimination. Mountains don't allow elimination of risk, only management of it. Accept that or stay home. Those are the options. No others exist, no matter what equipment you carry, no matter how much training you have, no matter how experienced you are. The mountain always has final say, the snow always decides, the weak layer always determines outcome. You just choose whether to be there when decision gets made. That's the terrifying truth about avalanches. Every type, every mechanism, all of them. Beautiful, deadly, indifferent. Waiting for the moment when conditions align and gravity wins and snow that wanted to slide finally does. Taking with it whoever happened to be standing in wrong place at wrong time, making wrong choice based on incomplete information about invisible weak layer formed weeks ago under conditions that no longer exist, but persist in snowpack waiting for additional load to exceed strength and trigger failure that propagates faster than human can perceive. Let. Alone react to resulting in burial under hundreds of tons of snow that seizes like concrete and crushes the breath from lungs and stops the heart and ends the story in the only way avalanche stories can end. With silence. With snow. With search teams probing. With families waiting. With data collected, with reports written, with lessons supposedly learned. Until next time, when someone else makes same choice, gets same result, becomes another data point, another case study. Another name, another story, another warning that probably won't be heeded because humans always think they're different, think they're smarter, think they're luckier, until they're not, until they're buried, until they're gone. Then they become the warning, the data, the lesson, for those who come after, who will probably ignore it. Like everyone before them did, like everyone always does, until the mountain teaches them, until the snow shows them, until they learn or they don't, survive or they don't, go home or they don't. That's avalanches. That's all of them. That's the truth. Cold? Hard. Buried under 50 meters of snow that fell at 290 kilometers per hour and killed. 31 people in 60 seconds in a green zone that was supposedly safe. That's the truth about every terrifying type of avalanche. Now you know.